I'm also just so you're all aware, I posted a few people had asked for like extra problems. So on Canvas, I posted some extra problems along with solutions. So if you're looking for extra problems to practice, that's a good place to find them. And I would encourage you to try the problems before looking at the solution, which is always a good practice. So that's there for you if you're looking for more practice. Let's see. So let's take a look at this function. Let's see, we have f of x equal to x squared plus 3 when x is less than 0. The square root of x plus 9 when x is bigger than or equal to 0 and less than or equal to 7. And sure, x minus 4 squared when x is bigger than 7. And our question here is going to be, where is this function continuous? So when you're asked a question like this, they're really ask you a much more specific question, but we have to kind of distill that down. And so what I want to point out here is, first of all, x squared plus 3 on its own, just a parabola. Continuous everywhere. We don't have to worry about it being discontinuous except for where we might change from this piece to this piece. Similarly, actually the square root of x plus 9 we need to be a little bit more careful about. The square root of x plus 9 is continuous as long as it's defined. So I'll just point out, if you look at y equal to the square root of x plus 9, it looks like this. It looks like the square root function, but shifted 9 to the, which way? Let's shift to the left or to the right. Here's, right, and correct. And here's how I think about it. I know that usually the regular square root function starts at the point 0, 0. Sorry, it's the square root of x, apologies. And I know that this one here, to get the same y value of 0, x has to be -9. So I'm shifting 9 to the left of where I was. So way over here at -9, 0 is where that function would start, and it would look like that and just shift it to the left. That's how I was thinking about it. It's like, what would x have to be to get the same y value? Oh, in this case, it has to be 9 less, so it's shifting 9 left. So this function I've just drawn in red here certainly is continuous as long as x is bigger than or equal to 9, which it certainly is if x is between 0 and 7. So there's no worry about discontinuity for this function on its own. Likewise, x minus 4 squared is another parabola. It's going to be continuous wherever it's defined. So really, the way this question is phrased, we're really only asking, is this function continuous at 0? And is this function continuous at 7? Because those are where we have the breaks. We know everywhere else it's for sure going to be continuous. We only need to check those two places. So let's check 0 first. Let me make sure I stay in frame here. As always, if I get out of frame, tell me, I'll move it up or down. 3 things. First thing, does f of 0 exist? Yeah, f of 0, we're putting sub in 0 in the appropriate place, and that's going to be for the middle piece, right? Because that's when x is equal to 0, and we're going to get the square root of 0 plus 9, which is the square root of 9, which is 3. Second thing, does the limit as x approaches 0 of f of x exist? Well, we have to do the two-sided limit here because we've got different functions on the left and the right of 0. So we're going to do the limit as x approaches 0 from the, I always like to pick the same side I've already kind of used first. So I know I've already used this middle piece. So I'm going to start with the limit as x approaches 0 from the right, because I know that's going to make me use the same piece when x is just a little bit bigger than 0. So that's going to be the limit as x approaches 0 from the right of the square root of, let me ask you all, should I write the square root of 0 plus 9 or the square root of x plus 9? I'll tell you, but I want you to use something. We should write the square root of x plus 9 because we're just replacing the function with what it's equal to. And then in the next step, we're going to actually plug in 0. We're not going to write the limit anymore, and we're going to get 3. So now here's kind of where everything that matters is going to happen. What about the limit from the other side? I think the limit as x approaches 0 from the left of f of x. Now which piece of the function am I using? The top piece, the middle piece, or the bottom piece? Yeah, the top, right? Because that's where x is less than 0. So we're going to do, it's an equal sign, believe it or not. The limit as x approaches 0 from the left of x squared plus 3. And just like every other time when we do a limit, if we can just plug in what x is approaching, we do. So we get 0 squared plus 3, which is 3. Which means the limit exists. The limit as x approaches 0 of f of x is equal to 3. And then finally, we should write something down at the end here, even though the conclusion might seem obvious at this point. Step 3, instead of asking, does the limit equal the function? I like to write down, yes, the limit equals the function, because they do. So we can say that f of x is continuous at x equal to 3. Sorry, at x equal to where? 0. So be careful. It's easy to accidentally confuse the x value with the limit value. So this is continuous at x equal to 0 because the limit as x approaches 0 of f of x is equal to the same thing that f of 0 is equal to. So that's the whole thing about being continuous at a point. The limit as x approaches that point has to equal the function value at that point. Questions about any of these things before we look at the other problem point? Come on in.
Can you use any of the equations for the f of 0 exists part, or?
No, we cannot. We have to use the piece of the piecewise function where x is defined to be equal to 0. And that's definitely the middle piece where x is bigger than or equal to 0. Other questions? Zoom people? Okay. Let's look at the other potential problem, which is 7. And I say problem, it's not really a problem, it's just maybe it's discontinuous there. So let's go ahead and look at x equal to 7. It is worthwhile to go through the same process. So first we're going to check part 1. What is f of 7 equal to? Let's see. So I'm going to plug in 7 to the middle piece again, because that's where the function is defined to be when x is 7. Actually, that's what the function is defined to be when x is 7. That's going to be the square root of 7 plus 9, which is the square root of 16, just 4. Second part, we're going to look at the limit. If we look at the limit as x approaches 7 from the left of our f of x, that's where we're still going to use that middle piece, because the middle piece is when x is just a little bit left of 7 or less than 7. So that's the limit as x approaches 7 of the square root of x plus 9. And then we can just be like, oh, we know what happens when we plug in 7 there. We just did it. Square root of 7 plus 9 is 16. Square root of 16 is 4. On the other side, the limit as x approaches 7 from the right of f of x. That's going to be the limit as x approaches 7 from the right of x minus 4 squared. Right, I'm just using the piece of the function where x is larger than 7. When I substitute 7 in there, I'm going to get 7 minus 4 squared, which is 3 squared, which is 9. Those left and right limits are not the same, which means the limit as x approaches 7 of f of x does not exist. And also, which means f of x is not continuous at x equals to 7. Because to be continuous, the function value and the limit value have to be the same, but the limit value doesn't even exist, so they can't be the same. To answer this question fully, right, we go back to the actually what the question was asking and say, okay, they asked, where is the function continuous? So let me ask you all, what's the only value where it's not continuous? 7. So we're gonna say it's continuous. If you're not sure how to write it using interval notation, you might just write words, right? Like if I was like stressed for time, couldn't figure it out, I'd write it's continuous everywhere except x equal to 7. But if we're trying to write it using interval notation, that's going to be, here's my number line. There's 7. The only thing I don't want, I want everything over here and everything over here. So this is continuous on the interval from -infinity to 7 exclusive union 7 to infinity. That's how we would write the interval of continuity. Come on in. Let's look at another example that's in the same vein as this, but a little bit different because there's something I want you all to see that I feel like is a fairly common, easy mistake. So let's look at this function here. Yeah, let's do that. F of x is equal to, it's going to have a number of pieces here. It's going to be x squared minus 9 over x plus 3 when x is less than -3. It's going to equal 5 when x is equal to -3. It's going to be, let me think for a second here. Sure. It's going to be, sure, let's do that. 2x when x is bigger than or equal to -3 and less than or equal to 1. And finally, and there's 4 pieces here, sorry, it's going to be x squared plus 1 when x is bigger than 1. It's kind of a lot, but let me zoom in a little bit just so we can see a little bit better. I know this part looks a little bit funky there. That's a, so again, x squared minus 9 over x plus 3 when x is less than -3, 5 when x is equal to -3, 2x when x is between -3 and +1, and finally x squared plus 1 when x is larger than 1. Cool. X squared plus 1 is continuous everywhere. Everywhere it's defined. 2x, also a polynomial, continuous everywhere it's defined. 5, also technically a polynomial. It's a boring one, it's a constant, but it's a polynomial. It's continuous everywhere it's defined. And x squared minus 9 over x plus 3 is a rational function, and it's only discontinuous wherever it's undefined. So this piece on its own is discontinuous at -3, but it's not even defined at -3. So as far as we're concerned, every function has no continuity concerns. The only concerns for this piecewise function are where we change from one piece to the other piece. And that is typical. Most of the time when someone throws a piecewise function at you and says, tell me where it's continuous, you're really only concerned about the things that are showing up over here. We're concerned about x being -3. We're concerned about x being +1, because that's where we're switching from one piece to the next piece. So let's look at whether or not this is continuous at x equal to -3. All right, so start off in the same way. We're going to check those 3 things. Let's look at f of -3. Well, f of -3 is easy. It's equal to 5. There's no other option. So, yeah, 5, right? Yeah, 5. Okay, now we're going to talk about the limit. So if I look at the limit as x approaches 3 from the right, approaches -3, sorry. -3 from the right, I'm going to use which piece of my piecewise function? The first piece, the second piece, the third piece, or the fourth piece? And it's not going to be the second piece because I'm not equal to -3. I'm a little bit bigger than the third. So I'm going to use the third piece here, which is f of x equal to 2x. So that's going to be the limit as x approaches -3 from the right of 2x. I'm just going to plug in -3 and get -6. Now I will mention, technically you could stop here. You could say, but you'd have to do some writing. You could say, well, I know that this function is discontinuous at -3 because either the limit's going to exist and equal -6, which is not the same as 5, and since those aren't the same, it's not continuous, or limit's gonna not exist, which means the function is also discontinuous. However, I think you should show the work of saying how it's discontinuous. And some of these people will ask you to say specifically in what fails to make this continuous. So let's continue on. We take the limit as x approaches -3 from the left-hand side of f of x. Well, now we're using the piece where x is less than -3. So it's the limit as x approaches -3 from the left of x squared minus 9 divided by x plus 3. And you'll notice that if we plug in -3, we do get 0 over 0. -3 squared is 9, 9 minus 9 is 0, -3 equals 3 is 0. So here is the situation where we have to do some factoring and canceling. So we're gonna write this as the limit as x approaches -3 from the left. The top factors is x plus 3 times x minus 3. The denominator is just x plus 3. X plus 3 divided by x plus 3 is just 1. So then we have the limit as x approaches -3 from the left of x minus 3. And then we plug in -3 and we get -3 minus 3, which is -6. So the limit does exist. The limit as x approaches -3, not from either side, of f of x is equal to -6. The reason I mention this specifically is because a lot of times people will see this, like, oh, the limit exists. That means it's continuous, but it's not in this particular case. The limit exists, but it's a different value than the function value. So here we're going to say that f of x is not continuous at x equal to -3 because the limit as x approaches -3 of f of x does not equal f of -3. They both exist. The limit exists, it's -6. The function exists, it's +5, but they're not the same. And what's happening here graphically is you essentially have a hole, right? This thing over here, in fact, we can draw the graph here. We have x squared minus 9 over x plus 3 looks like x minus 3. Which kind of looks like sorry, I'm giving myself not a lot of great room for my graph here. Kind of looks like this. There's the piece of my graph that is left of -3. And then when x is equal to -3, the y value is 5. And then when x is to the right of -3, the graph looks like 2x. So it's got a slope of 2 now. So it's going to go something like that. All the way up until 1. So that's what my graph looks like. So, oops, sorry, you can't see all that. Apologies. That's what my graph looks like so far. Here's the piece that's left of -3. Here's the piece that's right of -3. But at -3, you've got this point way up here. So definitely discontinuous at -3. Limit exists. It's -6. You got a hole at -3, -6. But the function is equal to 5. So discontinuous at that point. Let's look at the other one. Let me zoom back out here. I know I'm kind of all over the place here. Okay, sorry. It's always a challenge. Maybe it's just me. Could just be me. Let's look at the other piece of this piecewise function. Or sorry, the other potential place where we might have discontinuity at x equal to 1. All right, so I want you all to try this one. So I want you all first to find f of 1. Second, you should find the limit as x approaches 1 by doing the limit as x approaches 1 from the left of f of x, which will be the limit as x approaches 1 from the left of this piece. And then you should find the limit as x approaches 1 from the right of f of x. I'll let you fill in which piece that should be. Go ahead and try that. Give it 30 minutes.
No, we're not using top function at all. So we're pushing one from the right. One is the function that's bigger than one. Which piece is that? Exactly, yeah. Sure. Okay. So here we're just trying to find, so we're not even doing the x is one part, right? So if x is approaching one on the left of 2 times x, what can we do to evaluate that? What are you using the first to do, right? Find it. Let me phrase it different. X is getting really, really close to 1. What's 2 times x? Really close to? Not 1. So let's see. So x is like 0.9, 0.99, 0.999, 0.9999999, and then 2 times x is like 2 times 0.9. 2 times 0.9. 2 times 0.999. It's really, really close to 2 times. So what we can do here, we're going to limit x which is 1 to 2x, so we can just substitute in x equal to 1 for the value of x. We can write this equal to, instead of 2 times x, 2 times 1. Because we're saying, oh, x is going to be really, really close to 1, we're just going to let x be 1. So finally, right. So
For f of 1, I asked the question over here, is f of 1 equal to 2 times 1 or 1 squared plus 1? Now, yes, I recognize those are the same numbers. 2 times 1 is 2, 1 squared plus 1 is 2. But for this evaluation here, we should definitely be plugging 1 into this third piece here where x is equal to 1. So we are going to write it as 2 times 1, which is 2. Now for the limit from the left, as x approaches 1 from the left, we're using the same piece because that is where x is less than or equal to 1. Specifically less than, we don't actually care about the equal to part. So we're taking the limit as x approaches 1 from the left of 2x. And just to remind everybody what this really, really means, right? I know we've gotten to the habit of saying you just plug it in, right? But really what you're saying is x is getting super duper close to 1 from the left-hand side. So for example here, if x is equal to 0.9, well then 2 times x is 2 times 0.9, which is 1.8. And if x is closer to 1, like 0.99, 2 times 0.99 is 1.98, I think. The closer and closer x gets to 1, the closer and closer 2x gets to 2. And so we end up being able to say you can plug in 1 because that's the shortcut we use. But really the idea here is that we're saying, oh yeah, x is just creeping up towards 1, and 2 times x at the same time is getting closer and closer to 2 times 1, which is 2. Same idea down here. Now if we look at the limit as x approaches 1 from the right of f of x, then we're taking the limit as x approaches 1 from the right of the piece of the function where x is bigger than 1. And you could ask yourself the same sort of questions, right? If x is getting closer and closer to 1 from the right, so x is like 1.01, 1.001, 1 point lots of zeros with a 1. If you take that number that's really, really close to 1 and then square it, that number is still really, really close to 1. It's actually even closer to 1. And if you add 1 to it, it's really, really close to 2. Now, we're actually just going to plug in the 1 to get 1 squared plus 1, which is equal to 2. But that's, again, the thought process. We're just saying, oh, yeah, x is getting close to this number. What is the function simultaneously getting close to? So now, you don't have to write this part, but I like to write the overall two-sided limit as x approaches 1 of f of x is equal to 2. And then since we see that the limit value is 2 and the function value is also 2, we can say, great, that means our function f of x is indeed continuous at x equal to 1, because f of 1 is equal to the limit as x approaches 1 of f of x. And then to fully answer the question, which was, where is the original function continuous? Well, we see that it's continuous everywhere except at -3. So our function f of x is continuous on the interval from -infinity to -3 parentheses to exclude it, union, and then we want everything to the right of -3, so -3 to positive infinity. Let's do one more continuity style question, and then we'll switch gears. There's one other type of question I feel like people often like to ask. Unless you all have unless there are specific questions you have about continuity, I'm happy to address those as well. Like if there's something that I'm not saying about continuity that you would like me to talk about, happy to say it. But now I'm like, let me look at that homework. Is she asking you where? Most of you are in Tavernettes class, right? Is anyone in Tamergalavi? Is anyone in the other person's class? Couple people. Okay. Definitely her homework assignment is, I think her homework assignments are good. They're worth doing. You should definitely do. I mean, they're also required, so you should definitely do them, right? They're not just worth doing, they're important to do. Same is true for Tavernettes class. I know they're not required and that you don't have to turn them in, but you should still think of them as being required, right? You should do all those problems, or at least enough of the problems to where you feel like you understand what's happening, right? If there's like 100 problems assigned for something, and after problem 50, you're like, okay, I've got this down, like you can probably skip the rest if they're repetitive. Well, let's look at something like this. Let's say our function f of x is equal to, and I'm going to steal this one, yeah. F of x is a times x plus 3 when x is less than 2. A times x squared plus b when x is between, when x is bigger than or equal to 2 and less than 3. And is equal to -5b plus 1 when x is larger than or equal to 3. So I just want to point out, first of all, each of the pieces of this piecewise function are continuous things on their own. The first thing is a line, it's some constant times x plus 3. The second thing is a parabola, it's some constant times x squared plus some constant. And the third thing is actually a constant, because it's just -5 times a constant plus a constant. So all those things are continuous on their own domains. And the question here is, what do A and B need to be so that f of x is continuous? So really what needs to happen here is all the limits need to exist, right? Because if the limits exist, they'll match up with the function values. But we need to make sure that what's happening from the left and right of 2 and the left and right of 3 are the same thing. Now, there's a couple ways people do this, and I kind of want to show you what I think it was the right way. So to be continuous at x equals 2, I'm not really going to worry about the fact that f of 2 exists. Right? I know that f of 2 exists. When I plug in 2, I'm going to get a times 2 squared plus b. Okay. What I'm really going to worry about more is we need the limit as x approaches 2 of f of x needs to exist. Now I'm going to now I'll show you the long way first. So what that means is we need the limit as x approaches 2 from the left of f of x to equal the limit as x approaches 2 from the right of f of x. So actually writing that out, the limit as x approaches 2 from the left is going to be the limit as x approaches 2 from the left of, I'm using this first piece right here, because that's where x is less than 2. So I'm going to get a times 2 plus 3. Oh, I did the thing I tried to tell you not to do. It's the limit as x approaches 2 from the left of a times x plus 3. And then I'm going to plug in the 2 and get a times 2 plus 3. I know it might not seem like a big difference there, but it is, in my opinion, an important nuance. On the other side, this should equal the limit as x approaches 2 from the right of f of x, which is going to be this middle piece right here. That's going to be limit as x approaches 2 of a times x squared plus b. And that's going to equal a times 2 squared plus b. What we're saying is these pieces have to equal each other for the limit to exist. So the limit as x approaches 2 from the left and limit as x approaches 2 from the right end up having the same value. Okay, now I've done this probably the longest way possible. The way people usually do this instead is they say, oh, well, I know if I approach 2 from the left, I'm just going to plug in 2 for x. And I know if I approach 2 from the right, I'm just going to plug in 2 for x. And so if I plug in 2 here and 2 here, I know those need to equal each other. So I can just set 2 times a plus 3 equal to 4 times a plus b. That's the limit from the as x approaches 2 from the left. That's the limit as x approaches 2 from the right. In a similar way, we can say the same thing about the limit as x approaches 3. If we think about the limit as x approaches 3 of f of x, what we're really going to do is plug in 3 here and 3 for x there. Oh, there is no 3 to plug in for x, which is fine. There is no x to plug in, that's okay. So we're going to set a times x squared plus, oh, sorry, a times 3 squared, apologies, plus b equal to negative 5b plus 1. And I should just point out this part here is the limit as x approaches 3 from the left of f of x. And sorry, I know that 3 there looks terrible. That's a 3. Tried to cover up my x with it, but it's not looking great. We can try a little harder there. And then this right hand part is the limit as x approaches 3 from the right of x. I should be a little more emphatic about that. If you have a limit as x approaches something and there aren't any x's to plug in your x into, that's okay. You're just going to get that value back. It's like when we take the limit of a constant, you just get the constant because the function is just flat the whole time. You're saying, okay, well, as x is getting closer and closer to something, this flat horizontal function is just keeping the same value the whole way. So it's getting closer and closer to the value that has been the whole time. All right, so here's what we've got. This turns into 9a plus b equals to negative 5b plus 1. So now what I would do is I would probably take these equations and isolate one of my variables in one of them. It seems like it might be easy to isolate this b right here. So if I subtract 4a from both sides, I can say that 2a minus 4a is negative 2a plus 3, and that's equal to b. And I'm going to take that thing that b is equal to and substitute. Well, I might simplify this equation before I do that, but I'm going to substitute this in for b over here. But first, I don't want to plug it in here and here. So let's be smarter about this and say, I'm going to add 5b to both sides and say that 9a plus 5b is equal to 1. And then plug in this for b down here. So I'm going to get. Oh, good. Yes, thank you. I'd like to pretend like I did that on purpose to make sure you're paying attention, but I did not. It's made a mistake. Yeah. 1b plus 5b is 6b. Good call. And if we plug in this expression for b, we're going to get 9 times a plus 6 times negative 2a plus 3 equal to 1. And now we should be able to solve for a. So distributing the 6, we're going to get 9a. 6 times negative 2 is minus 12a. 6 times positive 3 is plus 18 equal to 1. 9a minus 12a is negative 3a. And if I subtract 18 from both sides, that's going to be 1 minus 18, which is negative 17. So a is going to be negative 17 divided by negative 3, which is positive 17 thirds. And then we can go back and substitute that in for a up there to find the value of b. So that means there's never enough room. B is going to equal negative 2 times a plus 3. Which is kind of gross, but we can write it out. That's going to be negative 34 thirds. And 3 is equal to 9 thirds. And negative 34 plus 9 is going to be negative 25 thirds. So those are the values that A and B would need to be to ensure that this function that we started with is continuous everywhere. Specifically at 2 and 3, but more generally everywhere. This is, I would say this is or at least used to be a popular flavor of continuity question on an exam. You would get something like this and that usually the numbers would be a little bit nicer maybe, but this is not an unreasonable question for someone to ask. Let me ask you all, are there other continuity things you would like me to talk about that maybe I'm overlooking? I know you might, and again, I know it's a hard question to maybe answer because you might not know what those are, but if there's anything that seems glaring to you, or just in general, it doesn't have to be about continuity, is there anything you'd like me to talk about before I move forward with other things? Okay, you can say it, Erica.
I'm trying to find it in the homework.
Sure.
But, okay, in the homework, in like the answer key part, there's stuff about relative extrema. Am I saying that correctly?
Oh, yeah, you are.
First derivative test, and then there are the maximum, that's my confusion.
Okay, and what section is that?
It was showing the 3.6 homework.
Really?
Yeah.
Interesting. So I thought they went. I mean, I know he does have some 3.6 stuff. Like I thought there was some 3.6, but I thought it was just about asymptotes.
The graph in there in astral.
Interesting. So I would say I can't imagine at this juncture you're actually expected to find those things because as you pointed, the first derivative test is required to find those things. So, or maybe, but it is true. So to find relative extrema, we need the first derivative test, which we haven't learned yet. So I would say as far as the graphing goes, if you're trying to graph something, I would focus on the intercepts and the asymptotes. So like, what's an example of something you're being asked to graph in that section?
It'd be like f of x equals x squared over x squared plus 9.
Cool, that's a great example. And so, oh, there's a chat, somebody in the chat here too. Let me not miss it. Closed interval continuity. Oh, sure, we can talk about that. Yeah. Yes, that's a yeah. I've got an example. Yes, Kelsey will do that one next. So this function here, I would point out a few things about it. First, let's look at the intercepts. The y-intercept, well, if I set x equal to 0, I'm going to get y equal to 0 over 9, which is 0. So 0, 0 is a y-intercept. It also means it's an x-intercept, right? If the origin is a y-intercept, it's also an x-intercept. There might be other x-intercepts though, so let's check. Find the x-intercept, we set the whole thing equal to 0. So x squared over x squared plus 9 equal to 0. We really just set the top equal to 0 because we're going to multiply both sides by the denominator and get x squared over x squared plus 9 times x squared plus 9 equal to 0 times x squared plus 9. I wouldn't normally show this much work. X squared plus 9 divided by x squared plus 9 is 1. 0 times anything is 0. So you get x squared equal to 0, which just gives us x equal to 0. So again, 0, 0 is an intercept. It's our only x-intercept, it's our only y-intercept. What else do we need to look for? Vertical asymptotes. How do we find vertical asymptotes? What do we set equal to 0 to try and find vertical asymptotes? Right, the denominator. I should say there is one exception to that statement, and that is if you have a logarithmic function. The natural log of x has a vertical asymptote when x is 0. Or more generally, if you're taking the natural log of 0, that value is going to make you have a vertical asymptote. Other than that, you find vertical asymptotes by seeing where you might be dividing by 0. So here, if I set x squared plus 9 equal to 0, I get nothing. There is no solution to this. You could try to solve it by subtracting 9 from both sides. If you do that, you get x squared equal to negative 9. And be careful here. I've seen many people over the years say, okay, so x is equal to the plus or minus the square root of negative 9, and completely just ignore the negative and say that that's plus or minus 3. It's not. The square root of negative 9 isn't 3. The square root of negative 9 is an imaginary number, which we're not going to talk about right now. So this is not real. There's no real solution to this equation. So that means we have no vertical asymptotes. What about horizontal asymptotes? I would encourage you, even if you already know what the answer is going to be, someone probably reading your work, if you're taking an exam, would like you to see that you find the horizontal asymptote by taking the limit as x goes to infinity. If you think about the shortcut for finding the horizontal asymptote here, what should my horizontal asymptote be? Right, I would even say 1/1 just to be explicit about it, but right, because I have a 1 times x squared there and a 1 times x squared there, and x squared is the highest power in the same highest power in the numerator and denominator. We know it's the fraction of those coefficients. If you wanted to show the work, which you might be expected to do on your first exam, we would divide everything by x squared and get x squared divided by x squared over x squared divided by x squared plus 9 divided by x squared, which simplifies as the limit as x goes to infinity of 1/1 plus 9 over x squared. And then we can say that since x is getting really, really large, 9 divided by something really, really large is getting closer and closer to 0. So we get 1/1 plus 0, which is just 1. That's the long way. Lastly, and I say lastly in that we're not going to talk about the derivatives here at all because we're not there yet, but if you were graphing this later on in the quarter, you would take the first derivative and you would use the first derivative test to determine if you have any relative extrema. But I'll say lastly, it's also worth considering any symmetry. Meaning, is this function odd or even? Or neither, right? Neither is usually the case, actually. So is this function odd, even, or neither? And here's how you check. A function is even if f of negative x ends up equaling the original function you started with. So you plug in negative x for all your x's, and then you simplify and you see if you get the same thing you started with. And a function is odd if f of negative x is equal to negative f of x. So you kind of do the same thing as if it's even, like you plug in negative x, and then you see if it's equal to the negative of the original thing you started with. So here, if we look at f of negative x, well, looking at my original function there, I'm going to plug in negative x for every x. So you get negative x quantity squared over negative x quantity squared plus 9. And when you square negative x, I really think it's beneficial to think of it as negative x times negative x. And you're like, oh yeah, a negative x times a negative x, the negative times the negative is positive, and the x times x is x squared. So we get x squared over x squared plus 9, which means the function is even, which means it has symmetry about the y-axis. So it looks like the same on the right as it does on the left. So now we're going to graph it. Now, when you're graphing something like this, it's okay to throw in some extra points, right? We don't have a lot of points. All we really have so far is that we know that we have the origin. Great. And we know we have a horizontal asymptote at 1. What's the equation of my asymptote? Y equals 1. And it's definitely good to write y equals for your horizontal asymptotes and x equals for your vertical asymptotes. Now, here's what I know. I know that as I move to the right or I move to the left, my function should get closer and closer to my horizontal asymptotes. I also know that I can't cross the x-axis ever again because I don't have any other x-intercepts. So really, it's probably just going to go kind of up like that. I might plot a couple more points. Like I might say, just for my own interest, if x was equal to 1, my y value is going to be 1/10. If x was equal to 2, my y value is going to be 4/13. I might even go a little bit bigger. If x was equal to like 10, my y value is going to be 100/109. So as we move further and further away, oh yeah, our values do get closer and closer to 1 because our fractions are getting closer and closer to the top and bottom being the same. And I should actually be more specific here. X could be positive or negative 1 and still get the same 1/10. X could be positive or negative 2 and still get the same 4/13. X could be plus or minus 10 and still get the same 100 over 109. So it's looking like it's kind of starting off slow and then eventually getting very, very close to that. And it's going to be the same thing on the left. So I will say that you could visually identify a relative minimum here. F of x equal to x squared over x squared plus 9 has a relative and actually absolute minimum at the point 0, 0. Because at the point 0, 0, the graph is lower than any other point next to it. Right? If you look to the left, the graph is higher up. If you look to the right, the graph is higher up. That means it is a relative minimum because it's smaller or lower than everything in its immediate vicinity or its local vicinity. So we call that a local minimum or a relative minimum because locally, right, just in its region, it's the smallest thing, or just in its region is smaller than everything relative to it. I will also say this happens to be an absolute minimum as well. This is the smallest value the function takes on for the entire graph. So it's also worth pointing out that it is also an absolute maximum, minimum. And again, I know these are words we can't really define yet, but that's really that's how you should think of a relative minimum or relative maximum. It's just smaller than all the things next to it or bigger than all the things next to it. Whereas absolute minimum or maximum means it's smaller than all the things or bigger than all the things on the graph. But normally, we don't have the tools yet to say that that's a relative minimum. So I don't think you're expected to do that yet. Let's look at, let's look at something like that. Yeah, what time? Okay, we got time. I do want to start talking about the limit definition of the derivative in a little bit here because that's definitely where we're going to be going. You'll probably when I see you all on Tuesday, be like, yeah, we talked about it Friday and Monday, and now we're doing the power rule. Potentially. We'll see. Okay, so let's do one more. Someone asked about closed interval continuity. So what if I said our function f of x was equal to the square root of 16 minus x squared? And I wanted to ask, where is this function continuous? And I'm going to tell you the thing I've told you already. Most functions are continuous on their domains. And that's going to be true here as well, but there's a little bit of exploring we have to do that is not super duper important, but it's a little important, so we'll talk about it. So let's find where the function is defined first, because that's what we are really concerned with. So one, where does f of x even exist? Well, we know how to find the domain of radicals. We're going to say we need the inside part of the square root, 16 minus x squared, to be greater than or equal to 0. And here's where it's easy to do this the hard way. The hard way, in my opinion, I wouldn't do it this way, is to bring x squared to the other side and say 16 is bigger than or equal to x squared, and then square root both sides. And the square root of 16 is 4. And what's the square root of x squared? Not quite just x. Almost plus or minus. I think I heard someone say it over here. It's the absolute value of x. I'll remind you of this because it's something that comes up not infrequently. What's the square root of 5 squared? Well, what's 5 squared? 25. What's the square root of 25? Okay. What's the absolute value of 5? Okay. What's the square root of -5 squared? What's -5 squared? What's the square root of 25? Okay. What's the absolute value of -5? Right. These functions do the same thing. If functions do the same thing and they have the same domain, they are literally the same function. So it is actually true that the function square root of x squared and the function absolute value of x are the same function. They take any input and give the same output. So they're the same. So you could solve this way, but I don't love solving absolute value inequalities. They're not impossible, but there's a better way. The better way to solve an inequality like this is to factor and use a sign chart. This is where I think the sign charts are actually really necessary. So this definitely factors. Now be careful here. Lots of people want to factor this as x minus 4 times x plus 4. And that is almost right, but not exactly right. Order does matter here. We have 4 squared minus x squared greater than or equal to 0. So this should factor as 4 minus x times 4 plus x. If you really don't like that, you can move everything to the other side. You can say, okay, well, I'm going to say that this is 0 bigger than or equal to positive x squared minus 16. And then you could factor it that way as x minus 4 times x plus 4. But I'm not going to do it that way. But you could do that if you want. So now, this should still be greater than or equal to 0. So now I'm going to draw my number line. And the important points that are going to go on it are positive 4 and negative 4. And then I'm going to test some points. So if x is larger than 4, like 5, 4 minus 5 is negative, 4 plus 5 is positive, and the negative times the positive is negative 4. This is good. This is a good practice to be in, because definitely when we start talking about finding the critical points and to find the relative extrema, you're going to be finding the critical points, putting them on the number line, and then using the sign chart to see if the function is increasing or decreasing. So that's why we're practicing. Another reason why we're practicing this now. If I pick a number between, well, I could pick a number between -4 and 0, like, sorry, -4 and 4, like 1, and 4 minus 1 is positive, and 4 plus 1 is positive, and positive is positive. Or I could have said 4 came from the 4 minus x factor, which has what kind of power? I know that it's 1, but it's odd or even. And when the power is odd, the sign, and when the power is odd, the sign changes again. So you could do it that way. It's actually a very powerful technique if you're comfortable with it. It's a lot faster than picking a point and plugging it in, picking a point, plugging it in, picking a point, plugging it in. We'll do another one in a second here. So this function, if I want 16 minus x squared to be greater than or equal to 0, that means I just want this part here and the endpoints. So our domain is the closed interval from -4 to +4. I will also graph this function because it's something worth graphing. It's something you should get comfortable graphing. If y is equal to the square root of 16 minus x squared, this graph has a very, very well-known shape. It might be easier to see if we square both sides and add x squared to both sides. Does this equation, x squared plus y squared equal to 16, look familiar? Right, it's the equation of a circle. The only difference between this and this is here, x can be positive or negative, and y can be positive or negative. Up here, when we take the square root of something, we only get out what kinds of numbers? Positive, right? Square root of 25 is 5, not plus or minus 5. So here, when you write it this way, y has to be positive. So we're only getting the top half of the circle centered at the origin with a radius of 4. So here is the graph of this function. It goes as far right as 4, 0. It goes as far left as -4, 0. And that point there is 0, 4. And it certainly looks like it's continuous everywhere it exists, with maybe one exception. Well, I should say with maybe 2 exceptions. So let's look at 2 different points and talk about continuity at them. So sure. So let's look at x equal to 3, which is right there. So does f of 3 exist? Of course it does. F of 3 is going to be the square root of 16 minus 3 squared, which is the square root of 16 minus 9, which is the square root of 7. Is that a real number that exists? Yeah, it's irrational, right? There isn't a nice decimal expansion of it that ever terminates, but it is a real number. It's a positive real number. It exists on the number line. It's somewhere between 2 and 3, but it's on there. Okay, second question. What about the limit? Well, the limit as x approaches 3 of f of x, since it's defined to be the same function on the left and the right of 3, we don't have to do a left and right thing. We can just say it's the limit as x approaches 3 of the square root of 16 minus 3 squared. Of x squared. I'm making the mistake I keep trying to tell you all not to make. And then we can plug in the 3 and get the square root of 16 minus 9, which is the square root of 7. So the function exists, the limit exists, and are they the same? For sure. So certainly f of x is continuous at x equal to 3. And really, we could extend this statement to any interior point of the domain. Meaning, really, we could have said this for any value of x in the open interval -4 to 4. So why are the endpoints potentially problematic? Here's why. Let's look at x equal to 4. So same questions. Does f of 4 exist? Yeah, f of 4 is the square root of 16 minus 4 squared. I should write the function over here. Sorry, the function is the square root of 16 minus x squared. So 16 minus 4 squared is 16 minus 16, so square root of 0, which is 0. Okay, here's where things require a little bit of massaging. What about the limit? Well, normally, for the limit to exist, we have to have the left-hand limit and the right-hand limit both be the same value. The left-hand limit's not a problem. The limit as x approaches 4 from the left of f of x, the limit as x approaches 4 from the left of the square root of 16 minus x squared. And if x is a little bit smaller than 4, like 3.9, 3.9 squared is a little smaller than 16. And 16 minus number smaller than it is a little bit positive. And we can for sure take the square root of a positive number and nothing's problematic. So we're just going to get the square root of 16 minus 4 squared, which is 0. Here's where the problem occurs. If we look at the limit from the other side, well, let me ask you. And let me do one thing before I ask you. Looking at the graph, if x is over here being bigger than 4, does the limit as x approaches 4 from the right exist? It's not even defined, right? The function isn't defined when x is greater than 4. It's not in the domain. So this limit over here does not exist. We can't evaluate it because if x is bigger than 4, x squared is bigger than 16, 16 minus 16 is negative, and we can't take the square root of a negative number. So here's the fix. The fix is we just say it doesn't matter. I'm really honest with it. We say that if a function is only defined on one side of a point, then we take continuity to be the function has to be only continuous from that one side. So here's what we're going to say. We're going to say since f of x equal to the square root of 16 minus x squared is only defined on the left side of 4, we only need the left-hand limit to exist and equal the function value. We only need the limit as x approaches 4 from the left of f of x to equal f of 4. And we have that. The limit from the left is certainly 0. F of 4 is certainly 0. So basically, if it looks continuous, it's continuous. If you look at the graph and be like, well, yeah, this graph certainly like, it doesn't look like discontinuous at 4. I don't have some weird jump or a hole or anything like that. It's just that it's not defined on the other side of 4. That is totally okay. So this function, we would say, is continuous on the entire interval. Closed -4 to +4. Even though at 4, it's really only left continuous there because the limit from the left is equal to function value. And at -4, it's really only right continuous there because the limit from the right is equal to the function value. And that's totally okay. And most people don't spend a whole lot of time talking about it because it's not that important. I think there's like a different example. No. That's all I think we really want to say about that one time. Okay. Yeah, let's spend these last 15-ish minutes, right? 10, 20 the time it's clock ends. Yeah. Okay. Let's spend these last 15 minutes starting to talk about the limit definition of the derivative. So let's say we've got the function f of x equal to, sure, let's pick an easy one, x squared. And we would love to know what is the slope of the line tangent to f of x equal to x squared at the point -1, 1. Draw this picture semi-decently. So here's our parabola, kind of like this. Yeah, that's all right, James. I'm trying to convince myself it's all right. Sure. And we are interested in knowing the slope of that line. Well, usually to find the slope of a line, you would need 2 points. And you would find the slope between the 2 points using the slope equation. So that's what we're going to do. We're going to take this point and we're actually going to throw in another point. It's actually not going to be the tangent line though. So what we're actually going to do is we say, well, here's our point, -1, 1, and I'm going to pick another point over here, like -2, 4. And I have a ruler. I love using my ruler. Do I have my ruler? Yeah, it's just hiding beneath all these pens. We're going to find the slope of this. Well, this isn't the tangent line that I'm drawing. Anyone know what the name of this line is? It's a secant line. So let's find the slope of that secant line. So the slope of my secant line that I've just drawn there, well, it's the difference in the y's over the difference in the x's. Sometimes it's nice to write a delta y over a delta x to remind us that the y's go on top and the x's on. It's easy to make the mistake of putting the x's on top because you see the x values first. And I've made that mistake too many times. So, and actually, before I find this, let me ask you all: am I expecting my slope to be positive or negative? Definitely negative, right? My line is going down from left to right. Definitely negative slope. So let's be careful here. It's going to be this y value minus that y value. So 4 minus 1 over. Now I have to make sure I subtract the x values in the same order. So I did 4 minus 1. So I'm going to do -2 minus -1. I could have gone the other way. I could have said it was 1 minus 4 over -1 minus -2. As long as I'm consistent, it's fine to go either way. In either case, I either get 3 over -2 plus 1, which is -1, or I get -3 over -1 plus 2, which is +1. Either way, you get -3 as your slope for that secant line. So now here's the idea. We're going to move that point closer to the point that we're actually interested in finding the slope of tangency, the slope of the tangent line. So let's say we're going to go over here to the point where x is -1.5 and the y value -1.5 squared. I'm terrible at squaring decimals, but I'm pretty good at squaring fractions. -1.5 is really equal to -3/2. And if I square that, Well, when you square a fraction, you just square each part. So that's going to be positive 9/4. Or if you prefer a decimal, 2.25. It's not always so nice, but at least when it's like a half, you can kind of square it pretty easily and not have too much trouble. So let's find the slope of this new secant line, which is closer to the slope of the tangent line. And again, my picture's starting to get a little bit bonkers here. So I want to find that slope of my blue secant line. It's going to be, let's see, now the difference in the y's. So 2.25 minus 1 over the difference in the x's, which is negative 1.5 minus negative 1. So that's going to be 1.25 on top. Negative 1.5 plus 1 is negative 0.5. I would really prefer to be using fractions here. 1.25 is 1 1/4 or 5/4. So I would write this as 5/4 divided by negative 1/2, and then multiply top and bottom by -2. You get 5/4 times -2/1. You could write the bottom part, negative 1/2 times -2/1. I don't think you need to write the bottom part because you know that when you multiply by others, well, that bottom part's just going to be 1. Negative positive 2/2, that's just 1. So I end up with 5 times 2 is 10/4 is 10/4, which is 5/2. So negative 5/2, or if you prefer, negative 2.25. 2.25, 2.5. Sorry. Okay, so our slope is still negative, but it's not quite as steep, which makes sense because if you look at the red line I've drawn here, it looks like it's less steep than the green line or the blue line. And it looks like if I keep moving this point closer and closer to my actual point, my slope should get less steep. How less steep? I don't know. So here's kind of the idea in practice. Ooh, have I drawn this in a weird way? Kind of. Oh, well, we'll deal with it. So draw this again. Hopefully not terribly. That's kind of terrible. So what we're going to do is we're going to say that we've got some other point out here. This point here is negative 1, 1. And this point over here, I'm just going to give it, I'm not actually going to pick a specific point. I'm just going to give it a different name. I don't usually like to use X because it's pretty standard not to. Usually we call this A, comma, and then the Y value. Well, if X is equal to A, the Y value is A squared. And A can be positive or negative. I don't have to call it negative A. I'm just going to call it A and just say that A could be a positive or a negative number. Here specifically, it looks like it's negative, but that doesn't matter. So I'm going to find the slope of this secant line between these 2 points. So let's see. So again, A squared minus 1 over A minus minus 1. Cool. So let's simplify this. I'm going to get A plus 1 times A minus 1 over A plus 1. Oh, look, I can cancel the A plus 1s. Because A, notably, A is not negative 1, right? It's a different point than when X is negative 1. It's, whoops, sorry. It's over here. So the secant line going through the point, negative 1, 1, and AA squared is going to have a slope of A minus 1. And now here's the reason we've been talking about limits so much. Because the idea here is, if I want to find the slope of the tangent line, so the slope of my tangent line, which let's write this in red, the slope of my tangent line, there's my tangent line right there. Well, I'm just going to let the A values get closer and closer and closer to negative 1. So the slope of my tangent line is going to equal the limit as A approaches negative 1 of the slope of my secant line. I'm just letting that point move closer, and the slope of the secant line Well, the secant line gets closer and closer to actually being the tangent line. And when those 2 points are super close to each other, the secant line is practically the same as the tangent line, and the slope is practically the same. So we can take the limit of this and look what's going to happen. We're going to get the limit as a approaches -1 of a minus 1, right? Because I've simplified this already as a minus 1. And then when I plug in -1, I get -1 minus 1, which is -2. And that's the slope of our tangent line. So what we can say here is the function f of x equal to -x squared equal to positive x squared has a tangent line with a slope of -2 at the point -1, 1. Often, the question that is actually asked for something like this is, what is the equation of the line tangent at the point -1, 1? So if we want to find the equation of the tangent line, well, we have all the pieces we need. The equation of the tangent line to f of x equal to x squared at the point -1, 1. To find the equation of a line, you need 2 pieces of information. You need a point, we've got one, and we need what else? The slope, which we just found. So we could say, I prefer to do it as the point slope form. So I like point slope where we do y minus the y coordinate equals your slope times x minus the x coordinate. And then solve for y. So you get y minus 1 equals, let's see, that's x plus 1. So -2 times x is -2x. -2 times +1 is -2. And then add 1 to both sides. So you get y equal to -2x. -2 plus 1 is -1. Or if you don't like that, you can start off with your y equals mx plus b, and then plug in your point and say, oh, well then 1 is equal to -2 times -1 plus b. So 1 equals 2 plus b. Subtracting 2 from both sides, you get b equal to -1. And then you can go back and plug that in and get that equation. Right, y equals -2x plus -1. Either way you want to find the equation line is fine. I like this, you might like that. Either way is good. So yeah, cool. So the general idea here is that we can find the slope of the tangent line of a function at a certain point by doing this process. Let me draw a more general picture here. And if you have questions, this is a great time to ask them. Now is also a good time. Anytime's a good time. Doesn't have to be when I'm pausing specifically, but if you have a question, just ask. So let's say we have some general function. It could be something like this. Here's my f of x. And the idea is we want to be able to find the slope of the tangent line at any point. Really what we're leading towards here is we're trying to find what's called a rate of change. When you're finding the slope of a tangent line, you're really saying, oh, how is y changing, the change in y, as x is changing, the change in x. That's what a derivative is all about. It's a rate of change. It's asking, how is one thing changing as another thing is increasing? How is your position changing as time is increasing? That's your velocity or your speed, your rate of change of position as time moves forward. So we're always just asking, how is the output changing as we increase the input, typically increase. So here, let's say I want to find the slope of the tangent line right there. So let's be smart and use your ruler. You have a ruler for a reason. So we are interested in finding the slope of the tangent line. And the way we do this, but let me see the picture better. The way we do this is in the same sort of way. So if I say that this is the point, come on, pens. So this is the point a comma f of a. What I'm going to do is I'm going to pick a point that's a little to the right of it. And we usually, there's a number of ways of labeling this. The fairly standard way is to say that this is a plus h. They might use a plus delta a or x plus delta x, but this is one fairly simple way of doing it. And this point here is a plus h comma f of a plus h. And what we're going to do is we're going to find the slope of that secant line. So we're going to draw the secant line. Maybe, yeah, sure. And so we want to know the slope of that secant line. And the slope of that secant line, just like whenever you find the slope of a line, it's, well, if you have 2 points, it's the difference in the y's divided by the difference in the x's. So that's going to be this y minus that y. So f of a plus h minus f of a all over that x minus that x. A plus h minus a. Now we should do one minor simplification here. We should simplify the bottom. A plus h minus a is just going to be h. Does that look familiar? It is exactly the difference quotient. That is why we have spent time simplifying the difference quotient, because simplifying the difference quotient is one of the parts of the process of finding the limit definition of the derivative. That's why we have talked about it. So that's the slope of the secant line. And then to find the slope of the tangent line, all you do is you take the limit. Well, you want this point to get closer and closer to that point. So you want the distance between those 2 points. What's the distance between those 2 points? If you go from a to a plus h, right? Or you can subtract a plus h minus a is h. You're going to take the limit as h goes to 0 of that slope of the secant line, which is just the limit as h goes to 0 of f of a plus h minus f of a all over h. And that is how we find the slope of the line tangent to f of x at x equal to a. That's the idea. And so what we're going to see moving forward is this is also how you find the derivative. And we're going to change, it's going to be a little bit, so like when we think about this, we think about finding the slope of the tangent line at a specific value of a, like a equal to -1 or +3 or whatever. And then as we move beyond that, we'll be like, well, a could really be any number, so let's just call it x. And then we'll find the slope of the tangent line at x, and we'll have the derivative as a function of x. So that's what we're moving towards. And then it's 10:21. I should end it there. See you all on Tuesday.